Hello students, in this topic we will discuss about multi-stage compressors. As the name indicates, in multi-stage compressors, the compression process taking place in more than one stages. In a multi-stage compressor, the compression of air from the initial pressure to the final pressure is carried out in more than one cylinder. It is used to get high pressure air for the end use. Usually in a compression process, the pressure ratio exceeds or the compression ratio exceeds 5, then the multi-stage compression is adopted. Now here this figure shows a schematic arrangement of two-stage reciprocating air compressor. This is called low pressure cylinder or LP cylinder. This is called high pressure cylinder or HP cylinder. In between these two cylinders there is an intercooler which is used to cool the hot air coming out of a LP cylinder, and it fed to the high pressure cylinder. The fresh air is sucked from the atmosphere in the low pressure cylinder. During its suction stroke, at intake pressure P1 and temperature T1, then the air compressed at a pressure P2 and then the temperature rises to T2. In the intercooler, the air is cooled at constant pressure. That means the pressure P2 remains constant, but T2 reduces to a lower value. In an ideal intercooler, T2 after intercooling is equal to T1. But this is not possible. The temperature of the compressed gas from the intercooler is always greater than T1. Then this high pressure, low temperature air supplied to the high pressure cylinder, in which the air is further compressed to a final delivery pressure P3. So this is intake pressure P1, this is the outlet of low pressure cylinder P2, pressure is P2, and this is the outlet of high pressure cylinder, which is the delivery pressure equal to P3. And this is the PV diagram of two-stage compressor. 1 to 2, this 1, 2, 3, 4 is the PV diagram for low pressure cylinder, and 5, 6 7, 4, 5 is the PV diagram for high pressure cylinder. Okay. Now the P1 is the atmospheric pressure or intake pressure. The air at P1 sucked to the low pressure cylinder, then compressed to a pressure P2. At point 3 the pressure will be P2. Then the temperature of air, compressed air, reduced due to the intercooling process, At point 5, the less temperature or low temperature high pressure gas fed to the high pressure cylinder, and it further compressed to a point 6 dash, that is the outlet of high pressure cylinder or delivery pressure. It is P3. So this is PV diagram of a two-stage compressor, and you can add one more stage here. Then there will be a intercooler between this high pressure and the third high pressure cylinder. Then again one diagram will get above this high pressure cylinder diagram. Okay. The compression process are normally assumed as a polytropic process, that is PV raised to N is a constant. In this figure, two PV diagrams are separated. This PV diagram is for low pressure cylinder and this diagram for high pressure cylinder, and this shaded portion is the work saved by the intercooler. Okay, that we will discuss later. So this is the low pressure cylinder PV diagram, this is high pressure cylinder PV diagram. Now these are the assumptions for deriving the expressions for multi-stage compressors. The first assumption is both suction and delivery pressure remain constant during the stage. Okay. The suction and delivery pressures are constant. Then the index of compression is same in all stages. The second assumption is index of compression, that is the compression is a polytropic process, so the polytropic index remains same in all the stages. Third one, the intercooling at each stage is at constant temperature, and the mass of air handled by the cylinders are same, that is mass flow through the cylinders are same. These are the four assumptions we used while deriving multi-stage compressor expressions. Okay. Now next is the work done in a multi-stage compressor. So we already assumed that all these processes are compression and expansion process are polytropic process. So we have already derived the work done in a polytropic process or a compressor which using polytropic process, that is this is the expression for work done. So work done in low pressure cylinder WLP is equal to N by N minus 1 into MRT1 into P2 by P1 raised to N minus 1 by N minus 1. This is for low pressure cylinder. Similarly, high pressure cylinder is N by N minus 1 into MRT3, because sorry, this what PV diagram is not the correct one. Okay, this is the correct PV diagram for two-stage compressor. From 1 to 2 is polytropic compression, that is in low pressure cylinder. 2 to 3 it is intercooling. 3 to 4 polytropic compression in second stage. 4 to 5 that is delivery stroke, and 5 to 6 polytropic expansion, and this cycle repeats in high pressure cylinder. In low pressure cylinder, 1 to 2, 2 to 7, that is low pressure cylinder or a low pressure outlet from the LP cylinder. 7 to 8, that is expansion in low pressure cylinder. 8 to 1, suction in low pressure cylinder. So this is the correct PV diagram for a two-stage compressors. So for high pressure cylinder 3, 4, 5, 6 is the PV diagram. So the equation will be n by n minus 1 into mr T3 into P3 by P2 raised to n minus 1 by n minus 1. So WLP is the work done by the low pressure cylinder and WHP is the high pressure work done by high pressure cylinder. So the total work done in a multi-stage compressor or two-stage compressor is equal to WLP plus WHP. So we will get this n by n minus 1 into mr is a common factor for both the equations. So we are taking it outside and the remaining part inside the bracket. Then assuming x is equal to n minus 1 by n, then we will get the total work is equal to 1 by x into mr into T1 into P2 by P1 raised to x minus T1 plus T3 into P3 by P2 raised to x minus T3. Here we have two cases. The first case is imperfect intercooling. That is the actual case. The perfect intercooling is the another case, but perfect intercooling, I already told you, it is not possible. Perfect intercooling means the temperature after intercooling is equal to ambient temperature or temperature of the intake air. That is not possible. So we discuss imperfect intercooling first, then we will go to perfect intercooling. So imperfect intercooling is the actual intercooling. The other one is the ideal case. So in imperfect intercooling, T3 is not equal to T1 or T3 is always greater than T1. And if you look at the previous expression, x m, that is mass, x is the ratio of n by n minus 1, m mass, r gas constant, T1 inlet temperature, T3 the temperature from the intercooler, P1 intake pressure, and P3 is the delivery pressure. So all these parameters are constant. We cannot vary any of these constants. I mean any of these values. Okay, they are constants. So to find an optimum value of P2, so differentiate with this equation with respect to P2 and equate to 0. That is dW by dP2 is equal to 0. You differentiate yourself the previous equation with respect to P2, then we will get P2 is equal to T3 by T1 raised to n by 2 into n minus 1 into root of P1 P3. Okay, this is the value of P2. P2 is the intermediate pressure, that is pressure outlet pressure of the low pressure cylinder or inlet pressure of the high pressure cylinder. Okay, in intercooler the pressure remains constant. The P2 is equal to, P2 before intercooling and after intercooling will be the same. Here is the second case, that is perfect intercooling. In perfect intercooling, I told you T3 or the temperature after intercooling is equal to the intake temperature T1. So if it is so, then P3 by T1 is equal to 1. Then we will get the value of P2 is equal to root of P1 P3. So in a perfect intercooling two-stage compressor, the intermediate pressure is equal to square root of inlet pressure and delivery pressure, product of inlet pressure and delivery pressure. And we can rewrite this like this: P2 square is equal to P1 P3, or P2 by P1 is equal to P3 by P2. Okay. So in a perfect intercooling, the pressure ratios of both the cylinder, if it is two cylinders, or all the cylinders in case of multi-stage cylinders, will be the same. Okay. That is, P2 by P1 is the pressure ratio of low pressure cylinder, and P3 by P2 is the pressure ratio of high pressure cylinder. So in a perfect intercooling machine, these two pressure ratios are same, and then in that case W is equal to 2 into WLP or 2 into WHP. Now if you consider n number of stages, okay, where n is the number of stages, then the pressure ratios will be P2 by P1 is equal to P3 by P2 is equal to P4 by P3, etc. C is equal to P of n plus 1 divided by Pn, where n is the number of stages. Okay. If there are only two stages, we will have P1 intake temperature, intake pressure, P2 intermediate pressure, and P3 delivery pressure. So we have three pressure values for a two-stage compressor. And if you have a three-stage compressor, we will have P1 intake pressure, P2 one of the intermediate pressure, P3 second intermediate pressure, and P4 is the delivery pressure. Therefore, if we have n number of stages, then the equation will be P2 by P1 is equal to P3 by P2 is equal to P4 by P3, etc. up to Pn plus 1 by Pn. Okay. Now, from these two equations, P4 is equal to P3 square by P2, and P3 is equal to P2 square by P1 from these two expressions. This expression, P2 by P1 is equal to P3 by P2, we will get P3 is equal to P2 square by P1, and from this we will get P4 is equal to P3 square by P2. Then P4 is equal to, substitute P3 is equal to P2 square by P1, then we will get P4 by P1 is equal to P2 cube divided by P1 cube. Okay. We are considering only this much, that is three stages. We will get delivery pressure divided by inlet pressure is equal to first intermediate pressure cube divided by initial pressure cube. Okay. So in general we can rewrite this P of n plus 1 divided by Pn, that is pressure, delivery pressure divided by it was not P1, it was Pn. Okay, now it is correct. P of n plus 1 divided by P1, that is delivery pressure of a multi-stage compressor divided by the initial pressure of the multi-stage compressor is equal to P2 by P1 the whole raised to n, where n is the number of stages. Okay. Also, if you want to find the intermediate temperature, we can use T2 by T1 is equal to P2 by P1 raised to n minus 1 by n. We have already derived this. Similarly, T3 by T2 is equal to P3 by P2 raised to n minus 1 by n, and so on. From this expression, we can also find the number of stages if you have delivery pressure and intake pressure. Okay, how many stages are required to get this much of pressure ratio we can find. Okay. Next is the advantage of multi-stage compressors over a single stage compressor. So this is a single stage compressor, this is a multi-stage compressor. The main advantages are the volumetric efficiency is improved by increasing the number of stages. That is the one of the main advantage of multi-stage compressors. The volumetric efficiency will increase. You work out this on this how the volumetric efficiency is improved by increasing the number of stages. I will ask a question on this in your internal examination. So you have to work out this how volumetric efficiency is improved by increasing the number of stages. The second one is a better mechanical balance can be achieved with multi-stage compressors. Third, work done per kilogram of air is reduced in multi-stage compression with intercooler compared to a single stage compression for the same delivery pressure. This is also very important. Okay, this also you have to work out yourself. Work done per kilogram of air is reduced. That is what I have shown in your first slide. That is in this slide. See, this shaded area is the work saved by the intercooler. So how this work is saved, that you have to write in your notebook by referring any of the textbooks. So this also I will ask in your internal examination. And the fourth one, see, reduce leakage losses. Leakage losses reduction because the pressure handling by each cylinder will be less compared to a single cylinder. So the possibility of leakage losses will be less in a multi-stage compressor. Lower operating temperature. Of course, using an intercooler, we can reduce the operating temperature and reduce the cost. So these are the some advantages of multi-stage compressors. So you have to write these two, that is first one and third one, and study well. Okay, our internal examination will be a online examination, I think, if college is not opened until the last week of this month. Okay, so last two modules, by this we have covered all the topics in the fifth module. So these two modules plus the portion taken in the next module will also be in the internal examination. It will be a online test and an open book test. Okay. So study well. All the best.